Hello, today I'll be covering how we can leverage information geometry in regularization to create a sort of anisotropic Fisher regularization. We'll be covering anisotropy through the matrix A, how our special case of L1 and L2 is technically just this matrix A, this general matrix, but Euclidean, how it can extend it to diagonal, and finally we'll talk about how we can use information for this. The problem with standard L1 and L2 is that it's Euclidean, meaning all directions are treated equally. There's no sense of which direction is more important and which one isn't. Equivalently, this is just A equals I, so directions are treated all the same. But in reality, in the real world, some directions are going to be more important than others. For instance, you might care about one direction more than another one. So how do we solve this? Well, we can use the matrix A. The matrix A is a general matrix that can define the geometry of regularization as long as it's PSD, or positive semi-definite. Simple L1 and L2 is a special case where A equals I, or it's Euclidean, that is. This is basically saying all the directions are the same because in the identity matrix, A equals I, everything does nothing, so everything's treated equally. A more sophisticated way would be to make this diagonal. So instead of everything being 1, some diagonal parts could be 3 or 2, or another one could be 15. And the value of this, the size of this, each element, represents how important each feature is. So as you can see in the formula below, that's the general form of regularization. We can see that it's just the magnitude, squared magnitude, or the complexity defined by the matrix A, in which case we can assume that L1 and L2 is a special case where A is just the identity. So just no, it's just the plain vanilla variant. But Fisher information provides a natural solution, pun intended. It's about how much information an observable random variable carries about the parameters. As you can see, the entire Fisher matrix is given by the formula, and then per entry, it's the expectation of the partial derivatives, and it's basically about how much information there is. So we're compiling all that into a matrix so that we can figure out which directions are the most informative and which ones not that informative. Okay, so how do we implement this idea? Well, then we can just set this general matrix A to be the Fisher matrix itself. That way, it's sort of like we're controlling the geometry or the metric of the regularization itself. We are applying regularization, but set in the space defined by Fisher information. While this is an incredibly powerful idea in the sense that being able to balance out which directions have the most information and which ones don't, and applying regularization, being mindful of that, the problem here is the Fisher information matrix is very hard to compute in reality because it's very, very computation expensive. So most solutions use the diagonal Fisher, where we just take the diagonal version of that Fisher matrix. Even though it's like an approximation, it's generally speaking, it's much more efficient than computing the other one, while still remaining very powerful. A key application of the diagonal Fisher generalized regularization lies in continual learning, where researchers discovered something called elastic weight consolidation. Here they use the diagonal Fisher to prevent catastrophic forgetting. So similar in concept, but it's like a different application to the field. And I'll be discussing elastic weight consolidation in future videos. I hope you enjoyed this. Thank you.